3.2 is about determinants and row operations. And the first thing I want to talk about here is complexity and how row operations affect determinants. So first up, cofactor expansion. We've looked at that, and one thing about cofactor expansion is it takes a long time to do it. If your matrix is small, then it's handleable. But if it's like a 5 by 5 matrix and you don't have a bunch of zeros in there, cofactor expansion is going to be painful and take a really long time. And we'd say the complexity of it is O of n factorial. What that means is, and n here is the number of rows and columns. So this means that if you have an n by n matrix, the amount of work or the number of operations you have to do to find its determinant using cofactor expansion is proportional to the factorial of n. And factorials grow crazy fast. So, doing a 5 by 5 matrix with cofactor expansion, that would be painful but doable. But it gets worse and worse as the size goes up. In fact, trying to do a 100 by 100 matrix would be impossible to do, even if you tried to do it on a supercomputer. The reason is, when I say it's impossible, it means it would take so long that it would take a supercomputer longer than the age of the universe to do that. Fortunately, there are better ways of finding determinants than cofactor expansion. Remember, finding the determinant of a triangular matrix is really easy. All you do is multiply all the numbers down the main diagonal, and the complexity of that is O of n, because all you're doing is, I guess, n minus 1 multiplications to get it. So the amount of work required is proportional to just the size of the matrix. So the plan is, it'd be nice if we could just convert a matrix from however it's given to us to triangular form. But there's a problem. If you take two matrices, A and its reduced row echelon form, they don't have the same determinant. However, the three operations that we use for putting something into reduced row echelon form, they have a well-defined effect on the determinant. And maybe I'm jumping the gun a bit by saying reduced row echelon form, because we don't have to get it into reduced row echelon form. We just have to get it into triangular form. And so if we do that and we keep track of the row operations, it's possible to define the determinant efficiently. And the complexity for that is O of n cubed. So n cubed, I mean, that's still going to take a while if the matrix is big, but it's not insurmountable. So let's look at the elementary row operations and what they do to determinants. Okay, if A and B are both square matrices, if B is obtained from A by swapping two rows, that just changes the sign of the determinant. If B is obtained from A by adding a multiple of one row onto another, that doesn't change the determinant. That's the one that's kind of surprising to me, but it's true. And if B is obtained from A by multiplying a row of A by a non-zero constant, that just multiplies the determinant by that same constant. And all these things are written in terms of rows, but it also holds true if it's done with columns. So let's look at a few examples here. It says use these properties and the fact that this determinant is 7. Let's use that to find these. Now each one of these matrices is something that I made by doing a row or a column operation on the original matrix. So let's look at this first one. 1, 4, 4, 3, 2, 1, 4, 4, 0. Okay, this original matrix, it looks like all we did here was multiply the bottom row by 4. So this determinant is going to be 7 times 4 is 28. This one, if you look at that, notice what's happening here is these first two columns are swapped. So swapping two rows or swapping two columns changes the sign. So this thing has a determinant of -7. This one over here, what's going on there? This one's not as obvious what's going on, but here's what's happening. If you take the bottom row multiply it by 5 and add it onto the middle row. That gives you 8, 7, 1. So adding a multiple of 1 onto another row, it leaves the determinant unchanged. What about this last one? We've got 1, 1, 0, 3, 2, 1, 1, 4, 4. The top and bottom rows were swapped, so that means that the determinant of this is the negative of the determinant of that. So I want to do a couple of proofs of showing you why these things work. But instead of doing them in general, I'm just going to do them on the 2x2 cases. For instance, let's look at, well, we know the determinant of ABCD is AD minus BC. Let's prove this last one. When B is obtained from A by multiplying a row of A by a non-zero constant, determinant of B is equal to C times determinant of A. All right, so this is A. Suppose B was equal to KA, KB, CD. So I multiply the top row by a non-zero constant, K. Well, this determinant then is going to be KAD minus KBC. So you can just factor the K out and you're left with AD minus BC. All right. If we swapped two rows, in this case there are only two rows, but if we put CD on top and AB on bottom, if you take that determinant, you get BC minus AD, which of course is the negative of this guy up here. And what the heck, let's do the other one as well. If you start out with the original matrix here, if you add a multiple of one row onto another, so let's take ABCD, let's multiply the bottom row by K and then add it onto the top. So the top row becomes A plus KC, B plus KD, and then the bottom row is still just CD. If we take that determinant, we should, according to the rule, get this original determinant. So let's see what happens here. When I multiply the diagonal, I get AD plus KCD. Let's multiply these guys. And then when I multiply those, I get minus BC plus KCD. So notice that KCD term cancels, and you're just left with AD minus BC. So basically, we've proven that these three rules work for the 2x2 case. Proving it for the 3x3 case would be a little messier. Proving it in general, you'd have to go back to the definition of determinant, and I'm not going to ask you to do any of those things. I just wanted to show you that this does indeed work. All right, so the next thing we want to talk about is using the row operations to find determinants and to do it efficiently, and we'll do that in the next video.